Okay, welcome back to another exciting video. This is section 15.4, more graph theory for weighted graphs. Last time we focused on minimum spanning trees. And this time we focus on a very different topic called the Chinese postband problem. And the reason why it is called the Chinese postband problem, or at least the Chinese part of that, is because it was first posed by a Chinese mathematician in 1962. And in order to lead up to this problem, we're gonna, as usual, have to throw in some definitions. But let's start quickly by reviewing some definitions that we already have. A walk, if you recall, was defined as any sequence of edges from any vertex I to another vertex, or to the same vertex, doesn't make a difference, but from any vertex to any other vertex. We call that a walk. A loop was specifically from vertex I to vertex I to the same vertex in one step. So you're here at a vertex and you just come back to the vertex. A cycle was a vertex to itself in any number of steps, in any number of steps. In other words, you can go through a bunch of other vertices before you get back to where you started. But for a loop or a cycle, your starting and ending vertices must be the same. Then we had a tree, which was a graph with no cycle. We had, and now we have some new definitions. So I believe that's all the definitions we had so far. So now we are going to define a new one. Let's throw in definition, and it says a trail. A trail is a walk that repeats no edges. So if you look at the definition that we've had so far, we've basically been focusing on vertices. Vertex this vertex to that vertex in one step, in more than one step, the same vertex, not having any cycles, which again involve vertices. But now we're looking more closely at graphs from the edge perspective. And a trail is a walk that repeats no edges. And a circuit is a trail that starts and finishes at the same vertex. That starts and finishes at the same vertex. So a circuit is now sort of a hybrid. It's a definition that incorporates this new one, trail, that involves the edges, but it also involves basically a circuit is a trail that's a cycle. You can really sum it up. It's a trail plus a cycle, right? It's got to repeat no edges, and you have to start and stop at the same location. Now, trails and circuits are great and all that, but we're going to go one step further. An Eulerian trail. And that's a very strange word, Eulerian. Like all the other words, trees, loops, cycles, walks, trails, circuits, these are all words that, are used in travel. Maybe not all the time, but they are used. So what is this Eulerian? And that's, by the way, I-A-N, not I-E-N. And Eulerian trail. So Leonhard Euler is the mathematician that really started graph theory with a very famous problem called the Bridges of Königsberg. And Euler was an amazing mathematician. He actually went blind during his lifetime. but knew that he was going blind. He was developing a condition, I think it was cataracts. So he taught himself to write neatly blindfolded, so that after he went blind, he could continue to write, even though he couldn't see what he was writing. And he ended up with, I believe, 27 volumes of mathematical work by the time he died. So very inspiring. But an Eulerian trail is a trail, first of all, that traverses all edges. So if it's a trail, no repeat edges, but you do every edge, we call it an Eulerian trail. Also an Eulerian circuit is a circuit. First of all, an Eulerian circuit is a circuit that traverses all edges. So an example of an Eulerian trail, here's a quick example of an Eulerian trail, would be something like this. So if you start here, vertex 1 to vertex 2 to vertex 3 to vertex 4, going along this direction, 1, 2, 3, 4, that will be an Eulerian trail because we traverse all edges. We repeat no edges, but we do not start and stop at the same location. Notice, by the way, in terms of degrees, the degree of this vertex is 2, the degree of this vertex is 2, the degree of this vertex is 1, and the degree of this vertex is 1. Because even though we're not going to prove it, we have the following extremely important results, which you basically just need to memorize and have down for your graph theory problems. And it's that an Eulerian circuit always exists in a graph if and only if all vertices have even degree. So when I look at a graph, if I look at every vertex and I check the degree and every degree is even, an Eulerian circuit is guaranteed to exist. An Eulerian trail will exist. Obviously, an Eulerian circuit encompasses an Eulerian trail, because an Eulerian circuit just has the added condition that we have to start and stop at the same vertex, but technically that's a trail as well. So an Eulerian trail, I'm going to write here, but not circuit, exists if and only if all vertices but 2, specifically 2, have even degree. So if I look at all the degrees and they're all even, I know that an Eulerian circuit exists. I still have to find it, but I know it exists. I just have to look for it. If I look at all the degrees and 2 of them are odd, then I know that I can form an Eulerian trail. And in that case, I'm going to write here, in this case, you must start and stop at the odd vertices. Okay, you must. So why is it called, so what is the Chinese Postman problem? The Chinese Postman problem says, if you're given a circuit, if you're given a graph, a weighted graph, because this is a section of weighted graphs, if you're given a weighted graph, what is the circuit, or at least trail, that you can traverse? In other words, you have to make sure you hit every edge that has the least weight. We want the minimum weight path through the graph that hits every edge. Now, if every degree is even, I know for a fact an Eulerian circuit exists. What does that mean? That means there exists a pathway where I cross every edge exactly once. Well, you can't get any less of a weight than counting each weight once. So if every vertex is even degree, it's straightforward. It's simple. If two vertices have an odd degree specifically, then I can at least form an Eulerian trail, where again, I can go from one to the other and cross every edge exactly once. You can't get any lower in weight than that. What happens if you have a different scenario? So let's do some examples. We're going to do one example and do exercise 15G, and then we're going to jump into exercise 15H. So one example, and then we're going to go directly into the exercises. So here's the example. It says solve the Chinese Postman problem, i.e. find a root of least weight for this graph that begins and ends at A, and find the total weight for this root. So here is A, and we can go here to B, and then down here to C. I'm drawing these graphs a little bigger because the bigger the graph is, as long as it doesn't get too big, I can really help me see what's going on. F connects to B, F connects to C, E connects to C, and then we have weight 4, 5, 6, 4, 5, 8, 7, 4, and 5. What's an example, by the way, in real life? Well, a postman, right, has a route. He's got to deliver mail along his route. He wants to walk all the streets of the route, or whatever the walk would be, whatever it is, in the least amount of time, in the least amount of steps. So this is very practical, very, I mean, these graphs are small, but on a larger scale, these are very practical problems. So the first thing we always want to do is look at the degrees of every vertex. This will help us solve every problem in this section. A has a degree 2. I'll put in parentheses here. B is 3. That's 1 odd. C is 4. D is 2. E is 3. That's a second odd. F is 1, 2, 3, 4. So if you look, there are 2 vertices of odd degree, which means I know that an Eulerian trail exists. But remember about Eulerian trails is that you need to start at one vertex and end at the other vertex. But we don't want to do that here. What we want to do here is start at A and end at A, which means we have to cross an edge more than once. It's just, there's no way out of it, because if we're starting and stopping at A, an Eulerian trail does not exist. Think about it. Look at B. B has a degree 3. We can come into B at one point and we can leave B, but then we come in again some other time, and how are you going to leave if you don't cut across it again? It's just not possible, right? That makes sense, hopefully. So we can't form an Eulerian trail here. We're going to have to cross edges more than once. So here's how we do it. Notice that there are 2 odd degree vertices, B and C, B and E in this case. What we're going to do is we are going to add extra edges to make it that all vertices have even degree. So how are we going to do that? We want to do that in the minimal weight possible. So we're going to look at B and E and look at every single path that connects them. In theory, there's infinitely many, but usually it's, you look at 2 or 3 of them and you can kind of just see which one has the minimum weight. For example, if I go this way and cut across that way, that would have a weight of 14. If I do this way, that has a weight of 11. And if I do this way, that would have a weight of 13. And if I come around this way, that has a weight of 17. It looks like the minimal weight would be the B to C to E connection. So what I'm going to do is I'm going to add extra edges that connect B and E. Now look, when I do this, B no longer has degree 3. B now has degree 4. E no longer has degree 3. It has degree 4. I have made even degree vertices out of odd ones. C also, by the way, has gone up, but it's gone up 2, so it's 6. Now everything's even. Because everything's even, I know for a fact that a root of crossing each edge once exists. And therefore, the minimum weight will be equal to, and I'm going to erase this in a minute, but it's going to help me count. 4 plus 5 is 9, plus 6 is 15, plus 5 is 20, 28, 4 makes 32, 37, plus 2 4s, so I'm going to add 8, and 2 7s, so I'm going to add 14. So this gives me a minimum weight of 59. So if the question is how to do it in the least amount of time, it might be 59 minutes. If it's the least amount of distance, it might be 59 meters, whatever the problem is talking about. But it also wants us to find an actual root. Well, we know it's starting at A. So let's just try it. Let's go this way. So A goes to B. B goes to C. C goes to D. D goes to E. E goes to F. Now, F is going to go to C, which is going to go to E, which is going to go back to C, which is going to go back to B, which is going to go back to F, which is going to go to A. So one possible root would be like that. And notice that as long as you give it a little bit of thought, there's no algorithm for finding the root like we had in the last section, Kruskall's algorithm, Prim's algorithm. It's more just look at the graph and just kind of find one. And usually it's not that hard. I mean, with these graphs, obviously, if you have a huge graph that have hundreds or thousands of vertices, you have a computer do it for you. All right, so now let's jump into exercise 15G. In exercise 15G, every single graph is going to have at most 2 vertices of odd degree, which we know how to handle now. What about if it's more than that? Well, 15H is going to deal with that. So let's do 15G and 15H. Question number 1. It says, solve the Chinese Postman problem for the graphs below, starting at vertex A. That means we want to have the traverse the graphs cutting across each edge at least once. And the Chinese Postman problem has the added question, or at least the added requirement of starting and stopping at the same location. Okay, so anytime you have the Chinese Postman problem, okay, it's to find the root of least weight around the weighted graph, and that returns to the starting vertex, like we had in this past example. So here's A, here's B, here's C, here's D, here's E, here's G, which is back to A, and G attaches to B, and also to F here in the center. G goes to F, F goes to B, F goes to C, F goes to E, but not to D. And now let's put in some weights. We have weight 8, we have weight 9, we have weight 7, 10, 6. This is question A, by the way. 6, 7, 6, 10, 5, 12, 11. It says state the edges that are repeated and the weight of the root taken. So we don't actually have to, oops, we don't actually have to find the root. We just need to know what, okay, sorry about that. So here A to B is 8, A to G is 9, this one's 7. Hi, F, technology is great when it works. B, and then to C is 10, and then to D is 6, and then to E is 10. F goes to C, F goes to D, D goes to G. This one here is 5, this one here is 12. And here's A. Okay, so we need to start at A and end at A and cut across each one exactly, not exactly once, but at least once. So we always start with degree. A is 2, great, even, I love it. B is 4, fantastic. Uh-oh, we have an odd. One odd, D is 2. Oh, this guy here is E, and E is 3. That's another 3. F is 4. G is 4. Okay, so that means we have no Eulerian circuit. If it was an Eulerian circuit, it's easy. You just do each edge once. This one requires repeats. Oh, and I left out a weight from C to F is 7. Okay, so the repeats are C and E. So what's the minimum weight connection between C and E? If I do CDE, that's 16. If I do CFE, that's 12. And I really don't see any other way, because if I go C to B, that's already 10. That's certainly going to be more than 12. So I have a C to F connection, that's that way, and I have a F to E connection. So the minimum weight is the sum of all the edges with 2 repeats. And those repeats, by the way, we could write it here because they did ask for it. The repeats are line segment CF and line set, not line segment, but connection CF. Doesn't have to be a line, and FE. In either order, EF, FC doesn't make a difference. So what's the minimum weight? Well, let's add it. So we have 8 plus 9 at 17, 24, 35, 47, 53, 63, 69, 79, and 10 makes 89, and 14 makes 103, assuming I counted everything correctly. So that's part A. Part B, we have the following. Here's F, here's E, here's D, here's B, here's A, here's C, and we have that connection there. Here's 20, 35, 45. Oh, there's an FD connection, that's 50. And then 45 down here, and 40, and 20, and 30. And same question, it's what's the minimum weight, assuming we started A and ended A, and what are the repeat routes that are taken. So let's start with vertices. 1, that's odd, B is 4, even, C is 2, even, D is 4, even, E is 2, even, and F is 3, odd. So we have 2 repeats. I'm sorry, not 2 repeats. We have 2 odds. A and B, we have to connect them. Well, obviously A has to go to B. It's got no choice. And then, of course, the easiest way from B to F might not necessarily be the one route, 35. What if these are like 2, 2, and 3? You can go a longer way around, so as long as the weight is less. But in this case, it is B to F directly. So what is the minimum weight? Again, we're going to just add them. What are the repeats? The repeats in this case are A, B, and BF. So what do we get? We got 20, 40, 50, 60, 70, 80, 90, 100, 110, 160, another 20. I missed that, 120. So I think 180 now. Let me just do it again. 20, 40, 60, 100, yeah, 180. That's 70 for 250. And then 90 gives me a minimum weight of 360. And now let's do C. So here we have A, B, C, D, E, F, back to A, also go straight across, diagonal this way, and straight across, not the other way. So we have 5 here, 4 here, 7 here, 6 here, 9 here, 7 here, 6 here, 4 here, and 5 here. Looks like that covers them all. Same question, starting at A. What's the minimum weight? And what are the repeats? So we start with the vertices, 2, 1, 2, 3, 4, 1, 2, 3, 1, 2, 1, 2, 3, 4, and 1, 2, 3. So it looks like F and C. So what's the shortest connection from F to C? If I go through B, that's 13. If I go through E, that's 13. If I do any other way, I get more than 13. So we have 2 choices. Either one works, doesn't make a difference. Let's just do this one here. FB and BC, those are my repeats. So the repeats are FB and BC, or I guess if you want to count the other possibility, even if we're not going to write it, FE, EC. Doesn't make a difference because we're repeating the same 13. And what is the minimum weight? Well, again, I just add them up. 5 and 4 is 9, 7, 16, but a second 7, 23, 23 and 7 is 30, 39, 45, 50, 56, and another 6 is 62, and 4, it looks like I get 66. So that's my minimum weight. Question 2. Explain why the following graph has an Eulerian trail, but not an Eulerian circuit. Okay, well, let's see what we have. We have A to B, to C, to D, to E, to F, to G, and back to A. We also have straight up from G to B. We also have F to B and F to C and CE. Nice little symmetric looking graph. So A, explain why the following graph has an Eulerian trail, but not an Eulerian circuit. Okay, pause as always. I should be mentioning it just to remind you. Well, it's all about the degrees. So let's see what we have here. A has degree 2, B has degree 4, C has degree 4, D has degree 2, E has degree, ooh, that's an odd. F is 4 and G is 3. Okay, well, why? Because there are 2 vertices of odd degree. Not exactly 2 vertices of odd degree. That's why. Part B. The weights in the graph. Oh, well, let's throw in the weights. Notice I didn't need the weights to answer part A because part A was all about whether an Eulerian trail or circuit existed, neither of which cared about the weights. But now it's asking a question about the weights, so now I have to include them. The question is, the weights on the graph represent the times taken in minutes for a postman to walk along the streets on his rounds, which begins and ends at vertex A. So starting and stopping the same location. If he walks down any street for a second time, it takes 1/3 of this time, as he does not have to deliver letters. In other words, the first time I walk down the street, I'm delivering letters, I'm stopping at every house, I'm putting it in the mailbox. But the second time I walk down the street, I'm just walking just to get from the first side to the other side. I don't have to actually stop and do anything. So we're going to find the time taken the process is going to be exactly the same. It's just the total time will be calculated slightly differently. So pause, try yourself. Okay, so where G and E are my odds. If I go through F, that's 30. Is there any other way to get from G to E in a faster way? And 12, 17, 9, that's more than 30. I don't see any. You should always give it the old college try, but I don't see any. So I'm going to assume that GF and FE, not assume, but it looks like GF and FE are the repeats. So what's the time? The time equals, or oh, wait a second. So I didn't read the question yet. Find the minimum length of time. This is part I of part B. Find the minimum length of time it could take for the postman to complete his round, and which streets would need to be walked along twice. It's exactly the same question. So 13 plus 12 plus 9. Notice this time I'm just writing it out. Plus 14 plus 16 twice. This is one of them. 13, 12, 9, 14, 16. I'm just going down left to right. 17, 23, 14 twice. Oh, actually, you know what? Whoops. I forgot the whole part of the question. It's not twice. It's 16 plus a third of 16 and 14 plus a third of 14. Because remember, those two only take twice, 1/3 the time. Plus 12, plus 16, and plus 14. Okay, I could do this, but I don't want to do this in my head. So I pass 13 plus 12 plus 9 plus 14 plus 16 plus 16 over 3 plus 17 plus 23 plus 14 plus 14 over 3 plus 12 plus 16 plus 14. And this gives me 278 minutes. Which ones are repeats? Would be GF and FE. That's part I, part double I. If the postman has to walk down both sides of every street, explain why no extra streets will need to be covered. If he needs to walk down both sides of every street, then that means I need to put in essentially an extra edge between any two vertices, one for one way, one for the other way. Well, now there's going to be twice as many edges coming out of each vertex as before. If there's twice as many edges coming out of each vertex as before, then that means every vertex is going to have even degree. If every vertex has even degree, we can make an Eulerian circuit, and therefore we don't have to do anything more than once. I mean, well, more than twice, because both sides. So that's the reason, because now there's an Eulerian circuit. Give a possible route that he can take. Okay, A to B, maybe not green. Let's do black. We'll be able to see it. A to B to C to D to E to F to G. Okay, and oh, I actually left out one of my edges here also. Okay, and back to A. Okay, now we're going to go back to G, that's this one, and then back to F along that one, and then back to E along that one, and then back to D along that one, and then back to C along that one. And then let's cut down to E, up to C, down to F, up to C, over to B, down to F, up to B, down to G, back up to B, and then back to A. Notice that there really wasn't much thought. I had to think a little bit to make sure that I didn't get stuck in a corner somewhere. But yeah, that's basically it. At least when there's two vertices of odd degree. Question number 3. The following graph represents bus routes between towns. So here's A, here's B, here's C, here's D, here's E, here's F, here's G, here's H, back to A, G goes to B, B goes to E. Okay. And the weights are the cost of the journeys in dollars. So these are the costs to get from one location to another location in dollars. A tourist staying at town A wishes to travel along all the routes and return to A, obviously as cheaply as possible. Find, for part A, find the minimum possible total cost. Well, as always, we focus on degrees. A has 2, even, I love it. B is 4, even, great. C is 2, great. D is 2, great. H is 2, great. F is 2, great. E is 3, and G is 3. Well, sorry, bud, you got to repeat. Well, what's the minimum cost to do that? Well, what's the cheapest way to go from G to E? If I go down through F, it's 11, but if I go up through B, it's 9. If I go around either way longer, it's going to be more than that, so I'm going to go this way. So what's the minimum cost? 5 plus 6 is 11, plus 3 is 14, plus 4, 18, another 4 because the double is 22, plus 5, 27, plus 6, 33, 5 and 5 is 43, 7 and 3, 53, and 6, $59. B. A new direct bus route, so let's remove those repeats. A new direct bus route is added between towns G and E. Explain why the addition of this route will result in a lower cost for traveling all the routes and write down the new amount. Well, G is no longer 3, it's 4. E is no longer 3, it's 4. Which means now every vertex is even, and therefore I can create an Eulerian circuit. Even if I can't picture it, I know it exists, which means I can cross every edge exactly once. So I don't have to do the repeat. The problem is that the question doesn't tell me what this new route costs. That's obviously a typo. It's obviously a typo. So I can look in the answers in the back, 15G. It tells me that the new route, there's an additional cost of $7, but a savings of $9, which means the new route must be 7. So now the min cost must be $57. Okay, lovely. So that takes us to the end of exercise 15G, and now we're going to go directly into exercise 15H. So what is it about 15H that makes things more difficult? Is that now you're going to have 4 vertices of odd degree. And hint, the only problems that you will ever see in an IB exam are 0, 2, or 4. You don't have to worry about odds, which can't exist anyways, because you can't physically build a graph that has an odd number of odd degrees because edges have to come in pairs, which means every edge that you add adds the total of all the degrees by 2, which means you can have 0, but if you add 2, you can't get an odd number of odd degrees. It just doesn't make any sense. So in this book, they're all 0, they're all 2 or 4. So let's do the 3 questions in exercise 15H, and that will finish 15.4. It says for each of the following graphs, list the 3 pairings. Well, let me first do it so you understand what I'm saying. So here's A, and here is B, and here is C, and here is D, and here is E. Up here is F, over here is G, here is H, and there is A. We also have H to B, H to F, H to I, here in the center, I to B, I to F, F to D, I to D, and B to D. Very symmetric looking graph, but the weights on the other hand are not symmetric. 6, 3, 4, 8, 9, 6, 4, 4, 3, 2, 5, 5, 6, 6, 7, 2. Okay, so let's start by, even before we do anything else, because we know we were in this chapter. I mean, the question could be, how many vertices are there? But it's not going to be. It's going to be a Chinese Postman problem. So let's go ahead and start by just looking at the vertices. So here's 2, 1, 2, 3, 4. Here's 5. Here's 2, 1, 2, 3, 4, 5, 2. And we got some symmetry going on here. That's going to be 5. That's going to be 2. That's going to be 5. And I here in the center is going to be 4. So what I can see immediately is that there's 4 vertices of odd degree. So what do I do? So question 1. For each of the following graphs, list the 3 pairings that connect 2 vertices of odd degree. So what are the 3 pairings? I can do B to H as well as D to F. That's one way of connecting each pair. I can do B to D and F to H, or I can do B to H and D to F. Those are the 3 ways that I can connect the odd vertices. So list the 3 pairings that connect 2 vertices of odd degree and find the minimum weight of the walk between the vertices in each pair. So let's take a look. If I do BH and DF, well, BH is going to be 4. B to H directly is 4. There's no faster or cheaper or smaller number that connects them. And D to F is not 6. If you go directly D to F, it's 6, but if you go through I, it's actually 5. DIF, if you go that way, it's 5. So that would be a total of 9. If I do BD, it looks like I get 5. And if I do FH, it looks like I get 6 for a total of 11. And if I do BH, oh, wait, BHDF, that's the same as the first one. Which one did I miss? BH, BD, and BF. Sorry about that. You're probably wondering, like, hey, what the hell is this guy doing? And that would be DH. Okay, so BF is 4, 3. Oh, yeah, it looks like BF is 7. And then DH, it looks like it's 6 for a total of 13. So list the 3 pairings that connect 2 vertices of odd degree and find the minimum weight of the walk between the vertices in each pair. In other words, the minimum weight is going to be 9. So I'm going to connect B to H with a extra edge, and I'm going to connect D to F with the double edge through I. And now I can go ahead and solve the Chinese Postman problem. It says find which edges need to be, oh, I don't have to do it. Which edges need to be repeated? Well, wonderful. So I have BH, I have DI, and I have FI. Okay, oof, good, that saved me a lot of time. Part B, same thing. Here's A, here's B, and that's 11. Here's G, and to A, that's 10. And then that's 9. And then here's C, and that was 8. And then C to G is 10. And then G to F is 12. And then F to C is 7. And then this way here is 11. Here's E. Here is C. Here is D. Here's 8. This is 13 there, and that's 9. Okay, so let's start with the edges, with the vertices, with the degrees. Yeah. So A is 2. Oh, we got an odd. 1, 2, 3. Another odd. 2. Third odd. Fourth odd. And okay, so we have 4 odds. So what are the options here? We have B, C, and E, F. We have B, E, and C, F. Or we have B, F, and C, E. If I do B, C, I get 8. And if I do E, F, I get 11. That gives me 19. B, E, B, E's a lot. 21. Yeah, so that's obviously out. BE is too much. B and E are too far apart. BF. BF I can do for 15. And then CE I can do for 13. That's going to be 28. That's too much. So the answer is 19. So I'm going to connect BC with an 8. And I'm going to connect EF with an 11. So what are my repeats? BC and EF. And we're done. Don't see anything that can beat those. Sometimes you just miss them. It's always nice to spend just a couple extra seconds to make sure. But I really don't see anything better than those. Okay, so that's question 1. All right, so let's get a little more challenging. Question 2. It says the graph below shows the lengths of connecting roads in a factory complex. So here's A, B, C, D, E, F, G, which connects to D, and to C, to H, which also connects to F, to I, which also connects to A, and then B and I, and B and H. It looks like that's it. And the weights are lengths. Oops, I looked at the wrong one. That's not 10, that should be 40. And 30, 50, 60, 80, 60, 40, 20, 40, 50, 40, 30, 30, 80. Okay, so A, find a route which minimizes the length of his walk. Oh, sorry. Each evening, a security guard walks along all of the roads and returns to his office at vertex A. So again, we have an A to A problem. Find the route which minimizes the length of the walk and state the length. Find the route and state the length. So we always start with degrees. A is 2, 1 to B is 4. We have an odd for C. We have an odd at D. We have even at 2. E is 2. F is another odd. G is even. H is even. I is odd. I have 4 odds. So what are my options? My options are CD and FI, or CF and DI, or CI and DF. Well, if I do CD, the direct route is 80, but if I go through G, it's actually 70. And FI doesn't look like I can beat 100. So that's going to be 170. CF, I don't see myself beating 90. And DI, is 110. That's 200, too much. And then CI is, looks like 110. And then DF is 70, 180. So we're going to go that route. CD through I, of course. Sorry, through G. And FI. So this is, those are the repeats. So first we want to find the root. So starting at A, let's first go to B. And let's then go to C. And then let's then go to D. Notice how I put little arrows in the graph when I traverse each edge so I don't forget one. And then we go to E. And then we go to F. And then we go across to G. And then to D. And then back to G. Then to C. And then back to G. Then to H. Then to B. Then to I. Then to H, back to I, and finally end at point A. And so again, notice that these lengths, they're not hard, just kind of walk along the graph. And what's the weights? 40 plus 30, I'm going to circle them as I do them. 40 plus 30 is 70, plus 50, that's 120, that's a 60, that's an 80, that's a double 60, that's 120. That's a double 40, so that's 80. That's a 50. That's a 20. That's a double 40, so that's 80. That's an 80. That's a double 30, so that's 60. That's a 30. That's a 40. Looks like everything is covered. So the minimum length is equal to 820, and they don't give me the units. We'll just say 820. Now, B. A friend offers to drop him off at one of the vertices and to pick him up at another. State which two vertices should be chosen to minimize the distance the security guard has to walk. Okay, so first of all, notice that this is no longer a Chinese postman problem because we're not starting and stopping at the same vertex, but it's similar. It's got connections, which is why it's in this section. What we have to realize now is if you're starting and stopping at two different vertices, then we don't have to make this into an Eulerian circuit, which every vertex is even degree. We can do it into an Eulerian trail scenario where two of the vertices have odd degree. Which two should have the odd degree? The ones that would have a minimum connecting length between them, because essentially, let me rephrase that. If I let two of the vertices be odd and the other two even, I can make an Eulerian trail, which is like the next best thing. So which two do I want to make even? The ones that if I connect them, it's going to give me the minimum weight. So it's the ones that you're connecting that I want to make into a minimum. And I have two choices. I can connect the C and D because that's 70, or I connect D and F because that's also 70. Either of them will have a repeat of 70 versus a repeat of what I'm currently doing, which is, it looks like 170. All right, C, D, and FI, I'm repeating 170. So I'm going to replace 170 with a repeat of 70. So I'm going to drop 100. So the minimum length is going to drop by 100, and it's going to go to 720. But they don't actually ask that. They just say, state which two vertices should be chosen to minimize the distance the security guard has to walk. So I'm going to connect, for example, sorry, which ones am I going to do? I'm going to connect, let's say, C and D with 70. So F to I is one option. Or if I connect D and F, C to I is the other option. Doesn't make a difference which one, as long as I connect. I want to make sure that's correct. Yeah. Yeah, because basically I'm going to do all of the edges once, and then the CD connection or the DF connection extra. Either way, it's a 70 extra connection. So either one works. You have your choice. Okay, and then finally we have the final question, question 3, which says, the graph below, let me first draw it. Here's A, here's B, here's C, here's D, here's E, here's F, here's G, here's H. Okay, and then we have an HG connection, BD connection, DG connection, DF connection. And that looks like the, oh, and we have an HF connection. That looks like the graph. So it says the graph below shows the roads that need to be taken by a postman when delivering letters. The weights on the edges, so let's throw them in, 38, 56, 88, 29, 40, 61, 32, 23, 43, 35, 26, 20, and 35. The weights on the edges are the lengths of the road in meters, and the postman needs to start and finish his deliveries at vertex A. So we have a Chinese postman problem. A, find a possible route he can take in order to minimize the distance he has to walk and state the length of this route. Fully justify your answer. Well, let's take a look. A is 3, B is 3, C is 2, D is 5, E is 2, F is 4, G is 4, and H is 3. That gives me 1, 2, 3, 4 odds. Okay, so what are my options? I can connect AB and DH, or AD and BH, or AH and BD. If I connect A and B, it looks like the direct route of 38 is the cheapest or the lowest, and DH would be 49 for a total of 87. AD is, looks like 43, and then BH is 73. It's not going to work. And then AH 35 is a direct route, but nothing beats that. And then BD 85, actually, not directly BD, but BCD would give me also too much. Okay, so it looks like AB and then DH through G would be the minimum weight to solve the Chinese postman problem. What is the length? So what is the length? Okay, well, we have 38 times 2. We got a 56. We have a 20. We have a 35. We have a 29. We have an 88. We have 23 times 2. We have 26 times 2. We have a 43. We have a 32. We have a 40. We have a 61. And we have a 35. Looks like the length is 613. You know what? I'm going to actually erase all those, but keep my answer, which is the length is 613. And now find a possible route. So it should be no problem here. A to B, B goes to C, which goes to D, which goes back to B, which goes back to A, which goes to H, oops, which goes to H, which goes to G, which goes back to H, which goes to F, which goes, let's say, up to G, which goes to D, which goes to F, which goes to E, which goes to D, which goes back to G, which finally returns back to A. Again, these lengths are not hard to find. Okay, and then part B. A friend offers to pick him up from vertex H at the end of his round and take him back to A. In other words, he does not have to go A to A, but rather only A to H. Explain why this would not decrease the length he would have to walk. Well, first note that if he's going from A to H, that means that we don't need an Eulerian circuit. We only need an Eulerian trail. But if I'm starting in A and H, I need to connect B and D. And how do I do that? I do that via, if I'm going to erase that and this and this, oh, I don't want to erase that. No, doesn't make a difference. Let's erase all this stuff here. So one bad thing about solving multiple problems of this type is that to really help see what's going on, we have to add arrows or circle numbers or something to the graph, and then you have another part which doesn't need them and kind of gets in the way. But in this case, B, C, and C, D, I would have to add. And then I have an Eulerian trail from A to H, no problem. But what did I just add? I added a 56 and a 29, which means I added 85 to the original graph. Right? 56, 66, 85. Okay, I just added 85. Now before, I had an 87 of additional steps, and now I have an 85. So did I miss a part? Are my numbers all correct? 23, 32, 60. Okay, so AB was 38 and DH anything beats that 49? I don't see it. So I think this is a mistake, to be honest, because what the book says is, yeah, if you do that, he would have to repeat BD, which is 88. Previously, he only had to repeat an 87 length, AB and DH. But this is not true. He does not have to repeat BD. He can do BCD, which is 85. So he'd be replacing an 87 with an 85, which should go down. So I'm pretty sure, you know what, let me check the errata page. I'll be right back. Well, it's not listed in the errata page, but I think it is. If his friend picked him up at H, then we can connect B and D with a root of 85 instead of the current extra of 87. No, I think this is a mistake. I'm going to stand by my statement. And then C, state where you would advise the postman to be collected in order to minimize the length he needs to walk and find the total length of the repeated roads in this case. So we know for H, according to the book, not a good idea. And even according to me, it's only saves him a little bit. So which one would be the best? And that seems to be that if we could have him do AH, which is the lowest at 35, or better yet, D is DH. Right, so he's starting at A, and he's going to end at either B, D, or H. End at B, D, or H. If he ends at B, he will have to do an extra DH. If he ends at B, he will need to do an extra BH. And if he ends at H, he will need to do an extra BD. Now, DH is an extra 49. BH is an extra a lot. B and H are way across from each other. And B and D is an extra 85. So BH is an extra, actually BH is an extra 73. If he does BAH extra 38 and 35. Actually, I just think I discovered why B was not a mistake, because I didn't look at every way of connecting B and D. There's actually a shorter way all the way around. Of 38 plus 20 is 58, plus 23 is 81. 81 is the cheapest, is the shortest BD. 81, which means, what was I saying? If he picks them up at H, we still have to do that 81. A friend offers to pick him up at vertex H, which means we would still need to do the extra BD. And the extra BD is, let me think about this for a minute before I just give a wrong answer. That actually doesn't help, because if he picks him up at H, I still have to redo BD, which is still a repeat of 81 and a repeat of 81 is still better than there was before, which was 87. So no, I still think it's a mistake. I'm going to still go with a mistake here. And then for part C, again, where should he be collected in order to minimize the length he needs to walk and find the total length of the repeated roads in this case? So again, he can end at 3 places, either B, D, or H. If he ends at B, he has to redo DH extra, which is 49. If he ends at D, he's got to redo BH, which is 73. I don't see a faster one than that. And if he ends at H, he's got to redo a BD, and BD is 81. So yeah, okay, so he wants to redo as little as possible. So he's going to want to redo the 49, and therefore the best bet is to end at B, not at H, but at B. So I still stand by my mistake for the middle part. Of course, I'll check that, but otherwise, that's it for 15.4. I will see you in 15.5.